Welcome back to the Bite-Sized Statistics video series. My name is Sean Rose, and you are watching the Continuous Outcomes route. This is Module 1, which covers t-tests, and this is the third video of Module 1, in which we are going to talk about violating some of the assumptions of the t-test and test how robust it is. So hopefully you are coming from video 2 in the t-test module, in which we actually opened up a Jupyter notebook and started playing around with running t-tests. We looked at a 2-sample t-test, we looked at a 1-sample t-test, and we did some plotting with ggplot and plotly and such. Now we're going to play around further with that same Jupyter notebook, but now we are going to play around with what happens when you use data that is not from a normal distribution, and how does that affect the type 1 error rate, and how does that affect the type 2 error rate. Okay, so let's jump over to our Jupyter notebook. So again, last time we got set up with the 2-sample and the 1-sample t-test. I'm just going to start off here by loading the packages we're going to need, which it's not yelling at me, so that means they're already loaded. Okay, so last time we covered sections 1 and 2 and 3. Yeah, we also talked about powering a 2-sample t-test. Today we're going to talk about sections 4. We're going to skip 5 because that's just reformatting data. That's of interest for you if you're wanting to basically pivot tables in R. We are going to talk very briefly about designing an equivalent Ftest to a t-test, because that's going to be a really nice lead into ANOVAs, which is the next module in the continuous outcomes route. But let's dive right in to the violating and testing assumptions section. So first, let's violate and test some assumptions with the 2-sample t-test. But instead of generating data like we did in the last video where we sampled from a normal distribution, let's instead sample from a uniform distribution. So if you think back to video 1, the theory underlying the t-test is that the null hypothesis is that we have IID normal random variables that we're sampling, and we actually have 2 populations, each having IID normal random variables for the 2-sample t-test, and with Welch's correction, the 2 populations are allowed to have unequal variances. But we're going to play around with what happens when we just totally break away from that assumption. So in this code here, I'm setting a seed just so the random number generator does the same thing every time. Setting the number of measurements to 8. By 8, I mean 8 measurements for the 2-sample t-tests. We're using this example we've been using the whole time where we have weights from 2 different cat breeds. This is going to be 8 measurements of weight from cat breed 1 and 8 measurements of weight from cat breed 2. And what we're going to do here is for 10,000 iterations, we're going to loop over and we are going to generate random data and then run a t-test. So this is generating random data where I'm sampling a uniform distribution 16 times, 2 times 8 times, with the uniform distribution covering the intervals 0 to 1, and then I'm just assigning those measurements to the 2 different cat breeds. The first 8 measurements I'm going to call cat breed 1, the second 8 measurements I'm going to call cat breed 2. I'm sampling the same uniform distribution for all of the measurements because I'm trying to look at type 1 errors here. So I'm going to actually assume the null hypothesis is true, i.e. I'm going to assume that all of the cats basically have weights that are sampled from the same uniform distribution. I'm then going to run a t-test using the same call we used last time. I'm setting var.equal to true, which basically means don't do Welch's correction. I'm going to knock that out actually because there's no reason to do that. Then I'm storing the p-value of the test just in an array that I'm calling p-vals. And then at the very end, after I've run all 10,000 iterations of that, I'm going to run what's called a binomial test on the p-values that I've measured. And basically I am just looking at, or actually I'm looking at the proportion of those p-values that are less than 0.05, meaning I'm looking at the proportion of p-values out of all of those 10,000 experiments I did. I'm looking at how many of in those 10,000 experiments did I reject the null hypothesis. So did I commit a type 1 error by falsely rejecting a true null hypothesis? And the binomial test is just going to spit out some stuff where it's comparing the proportion of tests I rejected a true null hypothesis to the desired proportion, which is 0.05. So let's run that. It's going to take a minute or 30 seconds because it is simulating 10,000 iterations. Actually, the reason I'm only doing 8 measurements per group here is just so this doesn't take forever because I'm lazy. But anyway, here is the results of the binomial test. So I'm looking at The number of p-values I got that are less than 0.05, it says number of successes. What that means is the number of times I actually falsely rejected the true null hypothesis. So 482 times I rejected the null hypothesis out of 10,000 trials. And that gives me an estimated proportion or an estimated type 1 error rate of 0.0482. That's just 482 divided by 10,000. It's also spitting out what I think is a Klopper-Pearson 95% confidence interval on that value, so don't worry about the Klopper-Pearson part. It's just a 95% confidence interval on this value, and it's saying at 95% confidence we think our type 1 probability, or our probability of a type 1 error is between about 4.4% and 5.3%. So what that really means is that despite the fact that I totally just mucked up the distribution and didn't follow the assumption of our data coming from a normal distribution, the type 1 error rate was actually almost entirely unaffected. It was 4.82 for 10,000 cases. I am 95% confident it's somewhere between 4.4 and 5.3%, which is really, really close to the desired type 1 probability, or probability of a type 1 error of 5%. So again, t-test showing how robust it is. But type 1 error rates are just one side of the equation. What about type 2 errors? So what about power, or 1 minus the probability of a type 2 error? Type 2 error, again, means accepting the null hypothesis when the null hypothesis is in fact not true. So to simulate that, what we're first going to do is we're going to run a little power analysis on the uniform distribution. So the uniform distribution from 0 to 1, turns out it has a standard deviation of 1 over square root 12. Honestly, I just looked that up on Wikipedia. You can derive it real quick if you want to. So I'm going to power the t-test, assuming I'm going to do num measurements, and that's measurements per group, so 8 measurements per group. And it even says that in the result, n is number in each group. I'm going to assume a difference in the means of the two distributions of 0.45, and then I'm going to plug in a standard deviation of 1 over square root 12. And when R is actually doing the power calculation here, it knows nothing about the fact that I'm using a uniform distribution. It's just looking at this and saying, I'm assuming that my two different populations have means that are separated by 0.45, and that the population standard deviation is 1 over square root 12, and then it's doing all its analysis assuming that those two distributions are normal, and then calculating t-statistics and such. Anyway, if I run the power analysis, what it's going to tell me is that the power of my test, if I have a mean difference of 0.45, and a standard deviation of 1 over square root 12, the power of my test is about 83-ish%, so close to 80%. So what I did in this next block of code is I'm doing that same essential Monte Carlo simulation, but this time I'm generating the weights, so my example data, from two different uniform distributions. The first cat breed is going to be pulled from a uniform distribution from 0 to 1. The second cat breed is going to be pulled from a uniform distribution from 0.45 to 1.45, so that the mean difference is this 0.45. Basically how I power, I'm designing this Monte Carlo simulation around how I powered my t-test. So I'm going to run that simulation, and then again, I'm going to knock out this. I don't know why when I wrote this code I was thinking we needed to not do the Welch's t-test, but I'm going to knock that out. And then we're going to compare the p-value that we get out, or we're going to compare our power at the end to what we expect the power to be based on the assumption of normally distributed random variables, and that power we expect it to be about 82.6-ish%. So I'm going to compare it to that with the binomial test at the end. Okay, so what does it tell us here? So it tells us that when we simulated data where the distributions were in fact different, two uniform distributions separated by 0.45, the number of successes, meaning the number of times we accurately rejected the null hypothesis, is 8,252 out of 10,000 trials. That means our power was 82.52% with a 95% confidence interval of about 81.8 to about 83.2. And again, we expected our power to be about 82.6%. So we actually, again, got really close. So it turns out, violating the assumption of having a normal distribution, or normally distributed random variables, violating in this specific way of instead having uniformly distributed random variables, it turns out that affected the type 1 error rate almost not at all, and it also affected the type 2 error rate, which is just 1 minus the power. It also affected that almost not at all. So in this next section, I'm going to violate the same assumption in a slightly different way. Instead of sampling from a uniform distribution, I'm going to sample the data from a t-distribution. This gets a little bit confusing as to like, well, why is that violating the assumption? It's a t-test. Well, remember, the assumption of the t-test is that my data is coming from IID normal random variables. The t-distribution arises as as the distribution of a statistic that I can calculate from those random variables. So here I'm going to actually make the samples be samples of random t-distributed random variables. So that's violating the assumption that the data is coming from normally distributed random variables. And I'm going to set a couple parameters here. Again, I'm going to do 8 measurements per group. I'm setting the t-distribution's degrees of freedom to be 3. The reason for that just has to do with keeping the variance. I didn't want to go too low in degrees of freedom because I wanted the variance of the t-distribution to be finite, and it turns out for, I think, less than 2 degrees of freedom, the variance of the t-distribution is infinity or undefined. So I set it to 3 for that reason, and I kept it low because I want it to be as far from the normal distribution as possible. And with large degrees of freedom, the t-distribution approaches a standard normal distribution. So I didn't want to do a large number of degrees of freedom and essentially not violate the assumptions that way. So anyway, again, the code looks pretty much identical. I'm just going to run 10,000 iterations. I'm going to sample, since I'm looking at type 1 errors in this first block of code, I'm going to sample all of my data from the same t-distribution and then split the data into 2 cat breeds. Then I'm going to run the t-test and figure out how many times I falsely rejected a true null hypothesis or committed a type 1 error, in other words. So let's run that. I should have been running that while I was rambling so that you guys didn't have to sit here and watch that run. But anyway, that is going to run in hopefully under 20-ish, 30-ish seconds. And then, well, yep, here we go. Let's look at the results. So we have 374 type 1 errors out of 10,000 trials. So our probability of a type 1 error was only 3.74% in this case, with a 95% confidence interval of about 3.4% to about 4.1%. So what we actually have here is a test that was overly conservative. We are rejecting a true null hypothesis less often than we actually expect to under the design of the experiment because of our violation of the assumption of a normally distributed random variable. Now that being said, it's not that horribly far off. I mean, it's not like we're rejecting it only 1% of the time. So, 3.74% versus 5%, not that huge of a deal. But we did here, by violating the assumptions of the t-test, actually create a type 1 error rate that is lower than what we would expect it to be by design. So what about power? Let's look at the exact same experiment we did with the uniform distribution, but let's look at what the power is when we use a t-distribution instead of a normal distribution. So again, I'm going to power the t-test, and it turns out that the standard deviation of the t-distribution is degrees of freedom over degrees of freedom minus 2 square root, so that's why that formula is here. I'm setting delta to be 1.5 times that, so a Cook's d essentially of 1.5. And it turns out that gives you a power, again, around about 80%. So I'm going to use that in the simulation for power. So here I'm doing some fancy stuff to calculate the so-called non-centrality parameter of the non-central t-distribution. So I'm going to have I'm going to sample from 2 different t-distributions. The first t-distribution is just going to be a t-distribution with 3 degrees of freedom centered at 0. The second one is going to be this t-distribution with a non-centrality parameter such that it is sitting with a mean, it's sitting to the right of 0 with mean 1.5 times the standard deviation of the t-distribution. So to do that, I have to calculate a non-centrality parameter, and again, I just looked up this formula on Wikipedia that basically converts the mean of the non-central t-distribution to the corresponding non-centrality parameter. Anyway, that's a bunch of details that you really don't need to worry about too much. It's just looking up a couple formulas. Again, here I'm going to generate weights, but this time I'm going to generate them from the 2 different distributions to be consistent with the power analysis. So I'm going to do t-distribution centered at 0, and then t-distribution with a non-centrality parameter that I calculated here, and then set the 2 different cat breeds. So the first num measurements is going to be cat breed 0, second num measurements is going to be cat breed 1. Then I'm going to run the t-test. I'm going to figure out how many times I accurately reject the null hypothesis. And then I'm going to compare the proportion of times I accurately reject the null hypothesis to the predicted portion, which is 0.7965 from the power analysis. So let's run that again. And again, I was a little bit dumb there and didn't run it while I was talking, so I apologize for that having to run here for a second. Next, we're going to actually look at the other assumption of the t-test, which, so it's not really an assumption because we don't assume it for Welch's t-test, but we're going to look at whether having unequal variances really screws up the t-test. Anyway, let's look at our results for the t-distribution. So number of successes, we got 7,697 accurate rejections of the false null hypothesis out of 10,000 trials. That gives us a probability or a power of 76.97%. Confidence interval is pretty tight again. And what did we predict? We predicted a power of 79%, but we're actually a little bit lower than that thanks to violating the assumption of normally distributed random variables. And that's actually kind of consistent with the issue with the type 1 error rate, where the type 1 error rate came out to 3.74%, so that's essentially an overly conservative t-test because we're not rejecting a true null hypothesis as much as we expect to be. We're also not rejecting a false null hypothesis as often as we would expect to be. We're a little bit underpowered compared to what we expect because of the violation of assumptions. But again, it's really not that far off. We're talking about 77% essentially versus 80%. So it's a tiny difference compared to what you might expect from violating these assumptions. So next, we're going to look at violating the assumption of equal variances for a two-sample t-test when we're running a classic student's t-test, so a student's t-test without Welch's correction for unequal variances in the two populations. So how we're going to do that, we're going to again set the seed. This time we're only going to do 6 measurements. I forget why I did that. It probably just gave a slightly different result. I'm setting the standard deviation of the first population to be 4, and then I'm going to set the standard deviation of the second population to be 10 times that of the first. So I'm doing a big difference in the standard deviations of the two populations. And then we're going to see how much that messes up the t-test. So I'm going to start running that this time to learn from past mistakes. Here I am setting var equal to true in the call to t.test. And that's so that we don't do Welch's correction to try to account for the unequal variances. Here in the actual generation of the data, you can see I'm sampling from a normal distribution with standard deviation equal to STD here, and then equal for the second population, I'm doing scale times STD, so 10 times 4 or 40. So here are the results of that Monte Carlo simulation. I falsely rejected a true null hypothesis 776 times out of 10,000 trials. That gives me a type 1 error rate of about 7.76%. Pretty tight confidence interval. So now I have created a t-test that is not as conservative as I would like it to be. And essentially I am rejecting a true null hypothesis more often than I would like to be. I would like to only be rejecting a true null hypothesis 5% of the time. I'm rejecting it closer to 8% of the time. So what happens if instead of doing the normal t-test, which does not try to account for this difference, which, by the way, I mean, we're talking about a factor of 10 differences in the standard deviation of the two populations. This isn't a minor violation of the assumptions of the t-test. This is a pretty huge violation of the assumptions of the t-test. And I find it personally kind of amazing that the type 1 error rate is actually still pretty reasonable. I mean, yes, it's a little bit less conservative than we would like it to be, but it's really not that far off. So let's now do the same thing, but with Welch's correction to try to account for these unequal variances. So the only difference between this code block and the last code block is that I got rid of this little flag var.equal to true. That's no longer in the call to t.test. And we're going to see what that spits out. And as you might expect, the probability of success here, or the probability of truly or falsely rejecting a true null hypothesis, is now only 5.3% with a pretty tight confidence interval, although it also actually includes the desired value of 5%. So essentially, Welch's correction worked very well. Instead of being a little bit under conservative, we are now being almost exactly as conservative as we want to be. We are committing type 1 errors about 5% of the time. I encourage, don't trust this too much in the sense of like, this doesn't imply the t-test always works no matter how you violate the assumptions. This is just, three specific examples where like, hey, look, violating the assumptions pretty terribly in some of them, like with the equal variances one, really didn't affect the type 1 and the type 2 error rates as much as you might expect. And I really just wanted to do this to point out, like, a lot of people early on when they're doing statistical analyses will look at things like QQ plots and they'll be like, oh my gosh, my data is not normal, I can't run a t-test. And I just want to give you an idea, and I encourage you to play around yourself even more with this. Try doing things where you combine having data with different distributions and unequal variances and see what the type 1 and type 2 error rates are for the t-test. And what you're really going to find is that the t-test is a lot more robust than you might initially think. So when you see tiny deviations from normality or tiny differences in standard deviation between two populations, things that are on the order of a factor of 2 and such, don't worry about it that much. That's really the big takeaway of this section, is that violating the assumptions of the t-test are really not as bad as you might think. I would even actually suggest you play around with generating data that comes from like bimodal distributions, because it turns out the t-test is even sometimes robust to some of that. Now, granted, again, if you actually run into data from a bimodal distribution in practice, I would suggest probably not running a t-test. But again, just play around with it and get a feel for it, because that's how, in practice, you're going to get a feel for when is it appropriate to run a t-test. So for the last little portion of this video, feel free to ignore this section entirely if you're not familiar at all with ANOVAs or Ftest, but I just want to demonstrate for people who are or who have heard of those things that you can pretty quickly design an Ftest either using linear regression or using the ANOVA function in R that gives you an equivalent to result to a two-sample t-test without Welch's correction. So I'm going to, in this line of code, this is actually copied from a code block earlier up, which is just generating our original two-sample t-test chonky cat data set, so back from section 1. So I'm generating data from two different populations. I'm sampling a normal distribution with mean 16, standard deviation 4 for the first cat breed, and then second cat breed I'm doing a mean of 16.8, same standard deviation. And then I'm going to design an Ftest from linear regression. Following this, I actually presented this, or no, I did not present this. I was going to present this in the theory slides and forgot to. But I'm going to generate a linear regression model using this data, where essentially I just let my linear regression fit the two means. So I let it fit a mean to breed 1, and I let it fit a mean to breed 2, and then I run an Ftest to compare the model of just fitting all of the cats with one mean to a model in which I allow the means to vary for the two different cat breeds. And then I'm going to run a so-called Ftest to figure out if my result is statistically significant. So either way, if you don't understand the details of Ftest yet, don't worry about it. That's the entire purpose of modules, the ANOVA module and the Ftest module in the continuous outcomes route. But I just want to show here that if I design a linear regression in this way, and then I compare it to a t-test, then I'm going to get the exact same p-value out of it. So I'm going to run that linear regression now. Linear regression gives me an intercept of 15.9562. The way I've designed the linear regression, that is the sample mean of the first cat breed. So if I go down and compare that to the t-test, I see that the group 0 mean is 15.95617. That's exactly what I got out of the linear regression. Then cat breed 1, the group mean is 16.668 from the t-test. In my regression, I actually designed my regression so that the difference between the sample means should be this value. So 15.9562 plus 0.7119 should give you 15.66808. So anyway, that's the result of the linear regression. Key point I want to make is that you run this little Ftest at the bottom here, and it gives you a p-value of 0.0434. And I want you to notice that is the exact same p-value that you get out of the two-sample t-test without Welch's correction. And that is because mathematically these two tests are actually equivalent. You can also generate Cohen's d for the two different tests. So this is Cohen's d from the Ftest. No, I think that's Cohen's d from the t-test actually. It's one of them. So yeah, it's the Cohen's d from the Ftest first, and then the Cohen's d from the T-test. So Cohen's d from the Ftest is 0.81814831. Basically, the numbers are the exact same thing up to a sign difference because of which one it considers to be the positive group versus the negative group. But either way, they're the same thing. Lastly, I want to show you that you can get the exact same result by using the ANOVA function, and this is what we're actually going to do in the next module, so I'm not going to go into detail of how it works, but basically, again, you can see that the probability of getting an F statistic of this value or greater is equal to 0.0434. That's the same p-value as we got before. So all of these things are related. You can also, if you're really, really excited about doing this kind of stuff, the multiple r squared and the adjusted r squared that are reported in the linear regression can actually be directly derived from this ANOVA table, so you can get them using the formulas I show here. So this number divided by this number, and then a little bit of a fancier formula to try to account for something that I'm going to talk about in later videos. Anyway, that's getting pretty off track, so again, if none of that makes sense, feel free to ignore it. It's not that important to the continuity of this series. With that, I'm going to end my discussion of this Jupyter notebook. I'm going to post this in the link below, and it's the exact same Jupyter notebook as the link that I've posted for video 2 in this module. So if you've already downloaded it, don't feel obligated to re-download it. It's literally the exact same file. So as always, thank you for watching this. It's been a lot of fun making it, and have a good one. Someday I'm gonna learn how to do this.